In this video, we'll introduce the concept of similar triangles. So to start, let's look at the three triangles below, A, B, and C. If I asked you which one doesn't belong, what would you say? You might want to make the argument that C is bigger, so it doesn't belong. But a lot of people have voted for B, and let's see why. If I look at A and C, they kind of look the same, just different sizes to each other. And if we explore why that is, it looks like this side and this side are the same length. And the same would be true for C. This side and this side look to be about the same. If I look at B, however, this side and this side appear different. This one looks a little more stretched out and is longer than the other side length. So in math, there's a fancy word for looks the same but has different sizes, and we call that similar. Let's look at a different argument focusing on angles instead. Let's say that I have a triangle with one angle that is 60 degrees and one angle that's 30 degrees. You have a triangle that has one right angle and one angle that's 60 degrees. Do we have the exact same triangle? Your gut reaction is to probably find that third angle. So in the triangle that I have, 60 and 30 means my other angle has to be 90 degrees. In your triangle, if I already have a 90-degree angle and a 60-degree angle, the only one that I could have left would be 30 degrees. So we have the same angles for sure. But does that necessarily mean it's the exact same triangle? Let me draw you a rough picture. Let's say this is mine. Here's my 90, this is my 60, and this is my 30. It's possible for you to have those same angles, but a totally different size. So angles are providing us that it's the same overall shape, but we don't know enough to know if it's the exact same without side lengths involved. So let's explore this concept of kind of the same, but not exactly. The concept of having things almost the same, but not exactly the same, is called similar in math. So if we look, there's kind of two opposite sides. We have congruent figures, which are the same shape and the same size. So if I look here, this side length is exactly the same as this side length. This side length would be the exact same length as this one, and then maybe this hypotenuse here would have to be the same as this one. So both corresponding angles and sides are congruent. And remember, congruent is like the geometric version of equal. If they are similar, they're that same general shape, but different sizes. So if we look here, those two triangles look to be about the same, and we see that the angles are congruent. However, sides are not. What the side lengths are, however, is a little throwback for you called proportional. So let's review what that means. Let's say this small triangle, we have side lengths of 3, 4, and 5. Proportional would mean that everything's growing at that same rate. It got stretched out by the same magnitude. So these look roughly doubled in size. So what that means for our side lengths is we would have to have 6, 8, and 10, where each side length also got doubled. So in this video, we'll be exploring the concept of similar figures and how to make an argument if triangles are similar or not. There's two different arguments you can make, one focusing on side lengths and one focusing on angles. So let's take a look. If I have information about the sides, what I want to try to prove is that my sides are proportional to each other. Where you're going to start is matching up pairs of corresponding sides. Remember, corresponding means it matches up in locations. So 3 would correspond to the 1.5, 4 would correspond to 2, and that 5 would correspond with the 2.5. So what I'm looking for is if 3 over 1.5 is proportional to 4 over 2, and if that's proportional to 5 over 2.5. Remember, things are proportional if they all divide to the same number. So what I'm looking for is 3 divided by 1.5 the same as 4 divided by 2, and are those both the same as 5 divided by 2.5? Here, they all equal 2. So that means they are proportional. So these triangles are similar, and the reason why is that the sides are all proportional. So that's the argument you can make for similarity based on side lengths. The other argument you can make is focusing on angles. So let's look at the two triangles we have. And both of them were given two angles. So in TRS, I have a 65-degree angle and an 80-degree angle. In LMN, I have an 80-degree angle and a 35-degree angle. Something that should stand out is that they each have 80 degrees, but we're given the other angle. So let's look at TRS and find what this missing angle would be. I could do a quick 180 minus 80 minus 65 to get there, and that would tell me that that missing angle is 35 degrees. I can actually stop there without having to find the missing angle of that third one. Since these two match, by default, these angles would have to match as well, since the sum has to be 180 in each of them. We call that the angle-angle criterion. And what it's essentially saying is as soon as you know that two are the same, that third pair has to also be the same. So here these triangles are similar since my angles are congruent. So here we have angles are congruent. Therefore, my triangles are similar. And I'm going to show you some fancy formatting for this. So I have triangle TRS and I have triangle LMN. The mathematical symbol for similar is this little swoop right here. So if you see that, that is saying triangle TRS is similar to triangle LMN. And the reason why is because the angles are congruent. So again, that fancy angle-angle criterion, what it's really saying is as soon as two pairs of corresponding angles are congruent, then the triangles are automatically similar because we know that third pair would also have to be the same. So let's do one quick example of each. If I'm focusing my arguments on the side lengths, the first thing I'm going to do is find those corresponding pairs of sides. So which matches up to which. So here I have a 6 that corresponds to a side length of 3. I have a 9 that corresponds to a side length of 4.5. And a 10 that corresponds to 5. I'm going to do a quick division on all of these and see that they equal 2. Therefore, they are all similar because I have proportional sides. Now the important thing to notice is that my top row all came from the same triangle. If you wanted to swap these and put the smaller numbers on top, that's okay as long as you're consistent. So if the top comes from one triangle, all of them should come from that same triangle. Now in the other example, I know nothing about the sides, so that can't be what I base my argument on. Instead, I'm going to focus on the angles. Hopefully what catches your eye first is that they each have a right angle. So that's one pair that I know are congruent. I need to know another pair also congruent before I make my statement that they are similar. What should next catch your eye would be these intersecting lines right here. We know that intersecting lines create some angles, and when they're across from each other like this, that means they're vertical angles, and vertical angles are equal. So these would be similar as well, and the reason why is that angle-angle criterion. I know that I have two pairs of congruent angles, so by default that third one has to be, which is why those two are the same general shape. If you're watching this from my math class, I want you to log on to Schoology right now and complete the quick similar or not intro. Good luck!